Good morning all. My name is B. Santhosh Kumar, Assistant Professor, Institute of Aeronautical Engineering. My subject is Computer Architecture. Today I am discussing about register transfer of micro operations. So, a digital system is an interconnection of digital hardware modules. The modules are registered, decoders, arithmetic elements, and control logic. The various modules are interconnected with common data and control paths to form a digital computer system. Digital modules are best defined by the registers they contain and the operation that performed on the data stored in them. So, when I'm going for the micro operations, move AX, BX, add AX, BX like this. So, into 03. I'm taking some small program. So, this micro operation, what the process is going on. So, when we entered the instructions in the micro operation, so we need a registers, A register and B register. Here A register and B register. So, how we are transferring the register to the memory or from the memory. So, a digital system is an interconnection of digital hardware modules. The modules are registers, decoders, arithmetic elements, or control logics. So, any of that one. Suppose I am taking, these are here registers. If I am taking decoders, so decoder means 3 into 2 cube means 3 into 8 decoder. So, n inputs, 2 power n outputs. That is a decoder. Arithmetic elements. So, arithmetic and logical we know that already. So, arithmetic elements are there. Suppose add AX, BX, move AX, BX, shift, mul, div, sub. These are the arithmetic elements or control logics I have to use here for the modules to the register transfer in the micro operation. The various modules are interconnected with common data and control paths to form a digital computer system. So, any of the interconnections of the common data, the control paths are to form a digital computer system. So, these digital modules are best defined by the register and they contain the operations that are performed on the data stored in them. So, what are the instructions I'm taking? These registers where you defined and where is the memory, and I have to go for the memory address of that one. So, where is the address? Memory address register, memory data register. So, every register I need a address and data. I need a address and data for that one. So, the operations executed on data stored in registers are called micro operations. A micro operation is an elementary operation performed on the information stored in one or more registers. The result of the operation may replace the previous binary information of a register or may be transferred to another register. Examples of micro operations are shift, count, clear, and load. Suppose the operation executed and the data stored in register are called micro operation. So, if I am taking add AX, BX, so the addition of two values, that is the two registers, the resultant value is stored in AX. So, AX is a resultant value. Yes, it is a resultant value. The resultant value stored in AX register. So, it is executed on data stored in registers are called micro operations. Okay. So, when the operation is completed, the resultant value is stored in a set of registers or register. The data stored in the register is called micro operations. A micro operation is an elementary operation performed on the information stored in one or more registers. So, not only one register, it is taking one or more registers. So, the result of the operation may replace the previous binary information. So, what is the previous AX value? Suppose here add AX, BX. So, I am giving here some A equal to 6, B equal to 5. Example I am taking. So, 6 plus 5 equal to 11. Where is the 11 value storing? It is storing in AX. But what is the previous value here? 6 is the previous value. But after the resultant value, the final value is stored in A. The previous value is replaced. Yes, the previous value is removed and the new value will be come to the new register. Okay, that is this one. The result operation is replaced with previous binary information of register or may be transferred to another register. The micro operations are shift operation, count, clear and load. So these are the micro operations of the register transfer. Shift means already we discussed in the previous shift left, SHL, SHR, shift left, shift right, circular left, circular right, arithmetic left, arithmetic right. So like this. So these are the shift operations and count equal to PC, PC plus 1 like this. We are counting the next value and clear means we are clearing all those bits. Insert clear like this. Load means we are loading the values of the registers. The internal hardware organization of a digital computer is best defined by specifying the set of registers it contains and their function, the sequence of microoperations performed on the binary information stored in the registers, the control that initiates the sequence of microoperations. Okay, any of the internal hardware organization of computer is specifying like this. First one, the set of registers it contain and their function. So any of the register I'm taking, it contain their function. What is the functionality of that one? Or are you taking which one? Which purpose? Move, add, like this. The sequence of micro operations are performed on the binary information stored in the register. So move AX, BX, add AX, BX into 03. So is it sequence or not? Yes, it is a 3 lines and it is a sequence. The sequence of micro operations performed on the binary information stored in the registers. Everything, every of the register is taking the binary values and the control that initiates the sequence of micro operations. So computer will take, suppose I am giving add AX comma BX, opcode, operand. So it will be define the address of this register. It will converting to the binary. Okay, converting to the binary. It will showing like this. Okay. So add AX comma BX, move AX comma BX like this. So opcode, operand. So computer registers are designed by uppercase letters and optionally followed by digits or letters to denote the function of the register. Example, the register that holds an address for the memory unit is usually called a memory address register, is defined by the MAR. Other designation for registers are PC, program counter. IR means instruction register of R1. Suppose any of the register, previously we discussed add, arithmetic means I am taking capital letters, add uppercase letters of add AX, BX. Move, I am moving the values of AX and BX and rotate ROT, AX comma BX. Here one example is taking here MAR, memory address register. So the computer designed by the uppercase letters, only uppercase letters, move, add like this. Okay, and to denote the function of these registers, the examples of these registers are memory address register, MAR. It is designed by MAR. Other designations of the registers are PC, program counter, PC plus 1, next program counting. Okay, instruction register. It will be what is the instruction of the micro operation. What is the first line of the micro operation? That is the instruction register. And R1 means register R1. The individual flip-flops in an n-bit register are numbered in sequence from 0 through n-1, starting from 0 in the rightmost position and increasing the numbers toward the left. The below show the representation of registers in that one. And taking here R1. What is R1 means? The register number is R1. R2. The register number is 2. That is a R2. The individual flip-flops in an n-bit registers are numbered in sequence from 0 through n-1, starting from 0 to the rightmost position, increasing the numbers towards the left. Okay, increasing the numbers toward the left. What is the first one? 0. Left one, 1, 2, 3, 4, 5, 6. So leftmost values are I am increasing. So that is a register or R1 and showing the individual bits. So here 0 to 7. Yes, 0 to 7. Total how many are there? 8-bit register. How can I know? Here we are indicated as 0, 1, 2, 3, 4, 5, 6, 7. But here in the first figure, register R1, but I don't know the size of this one. But we have to find out R1. What is the size of this R1? But in the figure B, it is showing clearly. Why? Because every bit it is showing the numbering 0, 1, 2, 3, 4, 5, 6, 7. So then we have to find out easily. So 0 to 7 means 0 to n minus 1. What is n here? 8. 8 minus 1 means 7. So 0 to 7 bit. 0 rightmost. It is a 0 is the rightmost. And n minus 1 is the leftmost. And also it is called MSB. MSB most significant bit. LSB least significant bit. So MSB is the most significant bit, LSB is the least significant bit. So when I'm taking the R1, it is the 8 bit. So 10, 10, 10, 10. So how can we define these registers? 10, 10, 10, 10. So it is a LSB and it is a MSB. So it is a least significant bit, most significant bit. The bit value is 0 here, first position, second position, third position, fourth, fifth, sixth, seventh. So 0 to 7 means it is a 8-bit register. The 8-bit register is R1. It is a one example. Here numbering bits. I am taking one example R2. 0 to 15. How much is there? 16-bit register. So R2 equal to 16-bit register 0 to 15. How can we show in the registers? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 and 16. So here I am defining as 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 and 15. So 15 bits total. 15 are there? Yes. So in the 15, in the previously we discussed 0 to 7 is the 8 bit. But now how many 16 bits are there? So 8 to 15 are another 8 bit. So 0 to 7. So here it is a LSB and it is a MSB. So 0 to 7 are the least significant bit. 8 to 15 are like this. Okay. So these are the lower order. It is a higher order. So here numbering logic from 0 to 15, that is a R2. So 0 to 7 is one and 8 to 15 is another one. It is a PC low. The most commonly using the registers are rectangular box with the name of registers and the individual bits can be distinguished. These are the Markov top-up box. Okay, it is a program counter L and H. L and H. So suppose I am taking AH equal to 16 bit. AL means lower order values means 0 to 7 of the 8 bit value and AH equal to another 8 to 15 bit. I am taking AH means 8 to 15 values. AL means 0 to 7 values. So AH means AX means 0 to 15. Total 16 bits are defining here. That is the AX. So finally AX equal to lower order values plus higher order values. ALH, AH plus AL 0 to 7, 8 to 15. So these are the higher order values. So 0 to 7 I'm taking as a PC of L here PC of H. So it is a 0 to 15. But in the previously we discussed here 0 to 7, R1 equal to 8 bit, here R2 equal to 16 bit, 0 to 7 and 8 to 15. So 0 to 7 means 8 bit. This 8 bit is a program counter of lower order and 8 to 15 is a program counter of higher values. And the 16-bit register, two parts are there. Bit 037 are the symbol L, means lower byte or lower order. 8 to 15 are the symbol H, means high byte. The name of 16-bit PC, the symbol PC 0 to 7 is the L, and the lower order byte 8 to 15 is the H to the higher byte. So PC of H and PC of L means 0 to 7, 8 to 15. Total how much? 16 bit. That is from 0 to 15. So PC of H plus PC of L equal to program counter. PC equal to 16 bit. 0 to 7, 8 to 15. The register transfer information transfers from one register to another is designated in symbolic form by means of a replacement operation. The statement R1 tends to R2 denotes that the transfer of content of register R1 into the register R2. So R2 gives to R1 means the R1 values 10101010. What is the data is there? It is shifted to R2. This data is transferred means loading. Okay, these are loaded means transferred to R2. That means the transfer of content from R1 to R2, R1 to R2, and it is replaced with the R2 by content of R1. So what is the data of R1? It is replaced with R2, and R1 is a empty. That means R1 does not change after the transfer. And if you want to transfer to occur only under a predetermined control condition, it can be shown by an if then statement. If P equal to 1, then only. Suppose R1 tends to R2. Is it any condition? No, there is no condition. If I want to apply the condition, that means if condition or like this. Okay, when if P equal to 1, then only R2 tends to R1. If P equal to 1, then only R1 data will be transferred to R2. R1 will be loading. R1 is loading. When R1 loading means P equal to 1. If P equal to 0, there is no transfer of data from R1 to R2. That is a condition. If required, we can take conditional, unconditional. So it is a conditional. If P equal to 1 means it is a conditional. It is a conditional. R2 tends to R1. It is a unconditional. It is a unconditional. So like this. So if you want to transfer an occurrence of under a predetermined control condition, then it can be shown to the if then statement. If P equal to 1, then only R2 tends to R1. And P is a control signal generated by a control section. So P is a control signal. The load is transferred from R1 to R2 or not, it will be controlling. And we can separate the control variables from the register transfer operation by specifying a control function. The control function is a boolean variable that is equal or 0 to 1, and the control function is included the statement P R2 to R1. So P R2 to R1, it is a control signal for conditional or unconditional. So it is about the register transfer of conditional and unconditional, and the control condition is terminated by a colon implies transfer of operation is executed by the hardware only if P equal to 1. Every statement written in a register transfer notation implies a hardware is construction for implementing the transfer. Below figure shows the block diagram that depicts the transfer from R1 to R2. So control condition terminated by a colon implies transfer operation to be executed by the hardware if P equal to 1. P equal to 1. Then R2 to R1. It is the conditional operation. So in the conditional termination of colon implies transfer of operation from hardware if condition p equal to 1. Every statement written in a register transfer notation implies a hardware construction for implementing the transfer. Below figure shows the block diagram. So we have to show here one example. Here control circuit is there, that is a P, and it is loading from R1 to R2 or not. It is a clock. Clock is a mandatory for loading the function. So if P equal to 1, is it a condition? Then only the load is enabled. Then only R1 to R2 is transferred. If load equal to 0 means, if P equal to 0 means there is no load. Then R1 to R2 will be transferred? No. This one means there is no data transfer. So if conditional, then load equal to 1. Then R1 to then R1 R2 tends to R1. If unconditional means control circuit is for conditional operation or unconditional operation. P equal to 0 or P equal to 1. If there is no condition means I am taking as a P tends to R2 to R1. That means P equal to control signal. There is no conditions for that one. R1 to R2 is loading. After completion of this one, loading will be disabled. It is a clock pulse is applied to the loading function R1. So 0, 1, 2, 3 like this. So it is a positive, negative, like this. So how many are there? There are so many. Transfer occurrence here, timing diagram. When load is enabled. When load is enabled means when starting from T to T plus 1. T to T plus 1 load is enabled. So load is disabled, remaining all load is disabled. When the load is enabled means R2 tends to R1. So remaining all it is not transferring. In this loading function means R1 is transferred the data to the R2. Okay. So what is the time duration means T to T plus 1. Okay. It is a load transfer. And the N output of register R1 are connected to the N inputs of register R2. The letter N will be used to indicate any number of bits for the register. It will be replaced by an actual number when the length of the register is known. And register R2 has a load input of this one activated by the control variable P. Suppose I am taking N outputs. That means register R1 are connected to the N inputs of the register R2. So what is the length? I don't know. Maybe it is 16, maybe it is 8. But it is 8 means definitely the 8-bit data transfer is to the 8. If it is 8-bit, this 8-bit transfer to the 16-bit. Remaining 8-bit will be empty. So that is the length of this one. So the letter N will be the used to indicate the number of bits for the register. So I am taking what is the length? R1 equal to N bit, 8 or 16. And the length of the register will be defined. And R1, R2, definitely we know that what is the length of this one. So N is defining as what is the length, what is the size of the register. So the register R2 has a load input that is activated by the control variable P. And it is assumed that the control variable is synchronized with the same clock as the one applied to the register. And the timing diagram P is activated of the control section by the rising edge of a clock pulse T. And the next positive transfer of the clock is T plus 1. To find the load input, activate the data transfer R2 is loaded into the register R1. So when the loading function is there, load is enabled. Load is enabled means R1 tends to R2. When, what is the time? Here, maybe T to T plus 1. So in the duration of T to T plus 1, the load is enabled. That means R1 data is transferred to the R2. Okay, that is it. And P maybe go back to a 0 at a time T plus 1. Otherwise, the transfer will occur with every clock pulse transition will P remains active even though the control condition such as P becomes active just after time T, and the actual transfer does not occur until the register is triggered by the next positive transfer of the clock is T plus 1. The basic symbols register transfer notation is listed below. So P maybe go back to the 0 at time is T plus 1. Okay, when the T plus 1 is came, it is go back to the 0 and it is starting from another register waiting for another one. And if it is P equal to 1, it is process completed. Next I will go for P equal to 0 at 0. and time equal to starting from t equal to t to t plus 1. Even though the control condition of P becomes active just after time t, the actual transfer does not occur until the register is triggered by the next positive transition of the clock pulse is t plus 1. And the basic symbols of the register transfer notation are listed in below table. We have to see here. Examples: MAR, that means memory address register, memory address register of R2. This, what is the R2? What is the address register of R2? It denotes a register and letters are numerals. Memory address register and R2. R2 is a register and MAR means what is the address of the register. And R2 0 to 7 and R2 is the L. So what is the meaning? L is the lower order values or not? Yes, L is the lower order values. Lower order, that is from 0 to 7. Yes, the R2 is 0 to 7 is the lower order values. Okay, a memory address register of R2. Here R1 transferred to R2. Yes, that the data of R1 is transferring to R2. Denotes that transfer of information, and it separates the two micro operations. That means R2 tends to R1 means the data of R2 transferring to the R1, and here R1 data is transferring to the R2. R2 data transferred to the R1 and R1 transferred to the R2. So two conditions are there. Yes, two separate. Each one or not belongs to other. Two conditions, two operations. Two operations are going on at a time. And A comma is used to separate two or more operations that are executed at the time. So here comma means at a time two operations are going on. Comma meaning. And T tends to R2 to R1, comma R1 to R2. Means at a time R2 data is transferring to the R1 and R1 data transferred to the R2. And it denotes an operation that exchanges the contents of two registers during one common clock pulse, that is t equal to 1. So when t equal to 1, then only two conditions are possible. If t equal to 0 means maybe the two conditions are not possible at a time. And these are the references of data transfer registers. Here we discussed today. A digital system is an interconnection of digital hardware modules. The modules are registers, decoders, and arithmetic elements and control logic. And the various modules are interconnected with common data and control paths to form a digital computer system. And the digital modules are best defined by the registers, and they contain the operations that are performed in the data stored in them. So the operations executed and the data stored in registers are called micro operations. Suppose I am taking add ax comma bx and move ax comma bx. So these are the instructions are performed by the micro operations, and these are the elementary operations performed on the information stored in one or more registers. The result of the operation may replace the previous binary information of a register, transferring of one data to the another. So what are the operations are performed? Shift, count, clear, and load operations are performed. And these are the rules for digital computer in the best defined by specific of internal hardware organization. First is the set of registers it contained and their function, and the sequence of micro operations performed on the binary information stored in the register, and the control that initiates the sequence of micro operations. And the computer registers are designed by a uppercase letters. So when I'm taking the instructions or micro operations, we have to define in the capital letters, uppercase letters. Okay. Example here taking MAR, memory address register, program counter PC, and IR instruction register, and R1 register R1. And individual flip-flops can be 8-bit register. Suppose 8 flip-flops means 8-bit register. Here R1 is there. How many flip-flops are defined? 0 to 7 means total how many? 8. So 8 flip-flops are used. What is the size of this register? Is a 8-bit register. If I am taking the 16-bit, how can we define? 0 to 7 is the lower order values, 8 to 15 is the higher order values. PC of L means program counter of lower order, PC of H program counter of higher values. 0 to 15, that is a R2. And the most common way to represent a register is by rectangular box with the name of the registers. And the individual bits can be distinguished. The numbering bits, 16-bit registers can be marking as this one. Here, PC of L 0 to 7, PC of H 8 to 15. So PC equal to PC of L plus PC of H 0 to 7 plus 8 to 15. That is a 16-bit register. So how we are transferring the register? How can you notate or how can you denote this one? R2 to R1 means the data of R1 is transferring to the R2. If you need any unconditional, then R1 tends to R2. If we need any conditional, then go for the conditional operation. If P equal to 1, then only it is possible. So then P equal to 1, R2 to R1. Is it conditional? It is a conditional. It is a conditional. If there is no condition means I am not giving any P equal to 1. Then it is a unconditional. So P is a control signal, generates by a control signal. We can separate the control variables from the register transfer operation of the control function. If control functions of Boolean variables are from 0 to 1. If P is the statement, P tends to R2 to R1 means the data of R1 is converted to the R2, transferred to the R2. So the control condition is terminated by a colon implies that it is a operation. Colon implies that it is a operation when P equal to 1 or P equal to 0 and like this for conditional operation. For conditional. And every statement written in a register transfer notation implies a hardware construction for implementing the transfer. The below figure shows the transfer from R1 to R2. R1 to R2 is transferring. The control circuit of P equal to 0, there is no load. If P equal to 1, then loading is there. What is the loading means? R1 data is loading to the R2. If P equal to 0 means there is no load, means R1 is stopping the transferring of from R2. So clock pulse is needed for transferring of the data from one register to another register. So I am taking the clock pulse from 0 to t plus 1 and transferring the function. When loading, it is enabled to the wave. If there is no load, means the wave will be not enabled. And the n outputs of the register R1 connected to the n bits of the register R1 and R2. N is the size of the register bit, 8-bit or 16-bit, and like this. P is a control signal or control variable to finding out the size. And it is assuming that the control variable is synchronized with the same clock at the one applied to the register, and P is activated the control section of edge at a time t. So P equal to activated when t equal to 0 or t to t minus 1. Okay, when P equal to 1. So P may be 0 to t plus 1, otherwise the transfer will occur at every clock pulse of P remains active, even though the control condition such as P becomes active just after t. The actual transfer does not occur until the register is triggered by the next positive transfer of the t plus 1. The basic symbols of the register transfer notation is listed. Here MAR, memory address register of R2, and R2 of L means lower order values of 0 to 7. R1 to R2 means it is an unconditional operation of register transfer R1 to R2. That is a transfer of information from one register to another. It is a separation. Means how can we know that? Means if comma is there, then two independent operations are performed. R2 to R1 and R1 to R2. These are the independent. One is not dependent on another one. And a comma is used for separate two or more operations are performing R1 to R2, R1 to R2 like this. So it is a references. Okay, thank you. It is about the register transfer micro operation.
Like, share and subscribe. Hit the bell icon for more updates.